Alright, in this lecture, we're gonna explain how to use stoichiometry and how you do problems in chemistry. Before I jump into a real stoichiometry chemistry problem, I actually want to take in a real life example and see how we actually use the stoichiometry in everyday life. Let's say I'm trying to make this pizza, and the ingredients that are needed to make one pizza would be one crust, 5 tomato sauce cups, and 6 cheese slices. And before we do anything else, we want to make sure we understand what this stoichiometry relation is. What that really tells us is one crust will be needed to make one pizza. So I can write this as one crust equals to one pizza. And the same can be said about the tomato sauce cups, which means 5 tomato sauce cups would be needed to make one pizza. So I can write that 5 tomato sauce cups equals to one pizza. And then I can also say 6 cheese slices would be needed to make one pizza. So that's your stoichiometry relation between the different reactants you have toward this product, which in this case is the pizza. Now we're told we have 10 crusts and 45 tomato sauce cups along with 55 cheese slices. And your job is to figure out how many maximum pizzas can be made. And when we say maximum pizzas, this is also called the theoretical numbers that can be made in this case, or theoretical numbers of pizzas can be made in this particular question. Now, when you just look at these numbers, we got 10 crust, 45 tomato sauce cups, and 55 cheese slices. Just don't go with the smallest number to be the one that's going to determine how much pizzas you can make. That's always that could always be incorrect. The smallest number does not necessarily reflect how much of the product you can make. You must do the stoichiometry relation before you can actually determine how much pizzas you can make. And when you don't know which one of those is going to be the limiting reactant, so limiting reactant means that one of them will run out first before the other two. And whichever runs out first actually determines the production, and in this case actually determines how many pizzas you can make. Um, and when you're just looking at it, just assume all of them are the limiting reactants, and you just do the calculations, and whichever makes the least number of pieces would be your limiting reactant. Starting with the first one, let's say I have 10 crusts. So if I using 10 crusts, I do know my stoichiometry relation between the pizza and the crust now. And I know one pizza would be made using one crust. So when you set it up like that, this crust cancels out, and at the end of the day, I would have 10 pizzas made in this particular case. Okay, I want to do the same thing with the other two ingredients and make my final decision after doing all the calculations. So I do have 45 tomato sauce cups, so I'm going to write down 45, and I'll probably just write down tomatoes sauce cups. So TSC stands for tomato sauce cups there. So 45 tomato sauce cups, and I do know the stoichiometry relation between the pizza and the tomato sauce cups is going to be one pizza divided by 5 tomato sauce cups. Okay, so the tomato sauce cups cancels out, and then you do this math, it's going to be 9 pizzas made. So now you can see how this 10 crust, even being the lowest number out of all the ingredients, were making 10 pieces, but this 45 tomato sauce cups actually making only 9 pieces. So far, seems like your tomato sauce cups is going to be the limiting reactant out of those two. But remember, you don't make your decision until you deal with all the reactants. So the third reactant you have, or the third ingredient you have in this particular question, is the 55 cheese slices. So let's do the math on that. So you have 55 cheese slices, and I do know the stoichiometry relation between the pizza and the cheese slices. I know one pizza is equal to 6 cheese slices, and when you set it up like that, your cheese slices will cancel out, and then that's going to be 55 divided by 6, and that comes out to be 9.17 pizzas. Obviously, you really can't make 0.17 pieces, but you can kind of see how the cheese slices would still make a little over 9 pizzas. So at the end of the day, your tomato sauce cups are the one that's making the least amount of pieces. So that's going to be your limiting reactant. So I could say my theoretical yield of the pizzas is going to be 9, and my limiting reactant is actually going to be the tomato sauce cups. Because that's the one that runs out first. And once that runs out, you really can't make the pieces. And obviously, to keep things simple, I just took those 3 ingredients to make these pieces. And obviously, you need more stuff to make a particular pizza. So just for the simplicity, I have only 3 ingredients in there. Now, that's a real life example. And if you don't understand this real life example, go back and re-listen to video before you moving on to an actual chemistry example. So let's look at an actual chemistry example. We have this equation here that has the nitrogen gas reacting with the hydrogen gas and making NH3, which is the ammonia. The very first thing you have to do is balance this equation. If you don't balance the equation, and if you go ahead and proceed by doing your stoichiometry with that balancing equation, your answer at the end of the day will come out to be incorrect. So you want to make sure you balance the equation, and even the equation that's given to you is balanced already, you still want to go back and double check if it's balanced or not. Okay, so it seems like I have 2 nitrogens on the reactant side and I have 1 nitrogen on the product side. So maybe I can go and start putting 2 in front of ammonia, NH3. That makes 2 nitrogens on both sides. And then I can see what happens to the number of hydrogens. So on the product side, I have now 6 hydrogens. So this 2 times 3 will give you 6 hydrogens. And I need to go back and make sure I do have 6 hydrogens on the reactant side. And right now I have only H2, which means there is only 2 hydrogens. So to make that 6 hydrogens, I would go ahead and put 3 in front of the H2. So that makes it 6 hydrogens. It seems like this reaction is balanced. Now, let's move on to the next step where we want to make sure we understand the stoichiometry relation here. The stoichiometry relation is going to be between the reactants and the products, and sometimes it's just between the reactants. I could say 1 mole of N2 is going to be making 2 mole of NH3. So that's one relation we have here. I could also say 3 moles of H2 is actually going to be equivalent to 2 moles of NH3. Okay, and in chemistry, whenever you're doing these stoichiometry relations, your moles is going to be the central point. If you're not given the moles in the problem, you want to make sure you must get the moles first. If you do the stoichiometry relations with the grams or with the liters, you're gonna get the answers incorrect. Your moles is the center point, so keep that in mind. You must have the moles before you do the stoichiometry relations. Okay. Uh, well, in addition, I can also say, in case if it's needed, I can also say 1 mole of N2 is going to be equal to, not necessarily equal, but you can say it's equivalent to the 3 moles of H2. All right, so sometimes you do need the relation between among the reactants, not just between the reactants and the products. Okay, well, let's look at this question here. We're told we have 10 moles of nitrogen gas, so we got 10 moles of N2 that's given, and we're given 25 moles of hydrogen gas, so that's going to be H2. We got to figure out what the limiting reactant is going to be, and we also got to figure out what the theoretical yield is going to be for the NH3 in moles. Okay, like I said earlier, if you look at two numbers, don't assume the lowest number is going to be your limiting reactant. You know, it may be the limiting reactants, but don't just take this for granted. Don't just assume the lowest number is always going to be the limiting reactant. It may not be the limiting reactant. You must do calculations using both of the reactants and figure out how much product you're going to make. And in whichever case you make the least product will be your limiting reactant. Okay, so let's start doing this problem where I'm already given the moles. So remember what I said earlier, when you're doing these stoichiometry relations, you must do those in the moles, all right? Don't do them in the grams and don't do them in the liters. As later on you may see the grams and the liters. You must do those in the moles. And the good thing here, the question actually already give you the moles, so you don't have to worry about converting your reactants into the moles. They are already in the moles. So let's start with the nitrogen. So if I'm starting out with 10 moles of N2, and I know now my stoichiometry relation between the N2 and the NH3, 2 mole of 2 moles of NH3 is equivalent to 1 mole of N2. So that's the stoichiometry relation. So that's why it's important to actually understand the stoichiometry relations beforehand. So moles of N2 cancels out here, and then that leaves you with 20 moles of NH3. All right, so that's going to be the theoretical yield if N2 is your limiting reactant. But like I said, I don't know yet. We got to figure out if the H2 is the limiting reactant. So we want to do the calculation now based on the H2. So if I start out with 25 moles of H2, and I know the stoichiometry relation, it's going to be 2 moles of NH3 with 3 moles of H2. All right, so when you set it up like that, your moles of H2 cancels out, and that leaves you with moles of NH3. Okay, so when you do this math, it comes out to be, you have 25 times 2, which is 50, and then 50 divided by 3 is going to be 16 point something. So I'll just do that math. It's going to be 16.7 moles of NH3. Okay, so based on those two reactants, it seems like H2 is the one that actually makes the least number of ammonia moles, which is going to be 16.7, even though we had a bigger moles for the H2 to begin with, it still came out to be the limiting reactant. So like I said, if you see a smaller number, don't just assume it's going to be the limiting reactant. You must do your calculations before you decide what's the limiting reactant. Okay, so to as of my final answer, my limiting reaction, so I'll write down as an LR, is going to be the H2, and my theoretical yield of H2, theoretical yield of NH3, that's going to be in moles, is actually going to be 16.7. Okay, if you had a hard time understanding this, go back and really listen to it before you trying this next problem. Okay, well, this next problem is actually similar. It says try again now. We are given 15 grams of nitrogen gas and 6 grams of hydrogen gas. Well, our starting point has been changed now. Our starting point is not um, the moles anymore. So if I just to kind of make sure I'm following the stoichiometry relations correctly, let me just go and write down the equation. So it's the N2 plus 3H2 makes 2NH3. So that was your original balanced equation. Now I'm given the grams of nitrogen, so I'll write down here and right underneath that is 15 grams of nitrogen, and I'm also given 6 grams of the hydrogen. And I'm trying to figure out the theoretical yield of the NH3 now in actually grams. Okay, we have to do the same procedure what we just did earlier. We have to do calculations using both of those reactants, and whichever makes the least amount of NH3 would be your limiting reactant. However, your starting point and your end point are different. In the previous example, your starting point was the mole and your end point was also the mole. Now in this case, your starting point is the grams and your end point, your theoretical yield also needs to be in the grams. So we got to make sure we get that taken care of. Well, if I'm given the grams, remember I cannot use the stoichiometry relations unless I convert these grams to the mole. So that's where the mole template, mole concept steps in. So remember how you convert the grams to moles. So I have 15 grams of N2 as my starting material, and then to convert this grams of N2 to the moles of N2, I'll put moles of N2 on the top and grams of N2 on the bottom so that the grams of N2 cancels out. And then what number goes here? When you're converting the grams to the moles, you use molar mass. So remember, 1 always goes with the moles, and the molar mass of nitrogen is about 28 grams. Now 1 nitrogen is 14. Since it's N2, it's going to be 28. So now you actually have the moles of N2, and you can relate that moles of N2 with the moles of NH3, because your moles has to be the central point. Okay, so then I would say 1 mole of N2 is going to be equivalent to 2 mole of NH3. So remember, this is the quality that we used in the previous example as well. So we have N2 cancels out here, and now we got the moles of NH3. Our last quality that we're going to have to use is converting these moles back to the grams. Remember, our final theoretical yield needs to be in the grams of NH3. So when you're converting the moles back to the grams, we still use molar mass or atomic mass or as our qualities. So we want to get grams of ammonia. So I want to put grams of NH3 on the top, and I want to get rid of moles of ammonia. So I'll put moles of ammonia on the bottom, and we're going to be using the molar mass here. So it's going to be 1 mole, and ammonia's molar mass is going to be about 17 grams, because remember, nitrogen is 14 and each hydrogen is roughly 1, so you can just take that as 17 grams. So when you do this math, every unit cancels out except the grams of ammonia, and that's what we're really trying to figure out here. So on the top we have 15 times 2 times 17, and then divide that by 28. So multiply the numbers that you have on the top and divide those numbers by whatever you have in the denominator. So that actually comes out to be 18.2 grams of ammonium. Okay, if we use up all the nitrogen, we would make 18.2 grams of ammonia. But like I said, we don't know if the nitrogen is the limiting reactant or the hydrogen is the limiting reactant. So we got to go back and do the same thing we just did for the hydrogen. Okay, so starting point for the hydrogen is going to be 6 grams of H2. And I know I need to convert this to the moles of H2 just like we converted the grams of nitrogen to the moles of nitrogen. So it's going to be 1 mole of H2 divided by grams of H2. And remember, the molar mass of H2 is going to be 2.01. Okay, so the grams of H2 cancels out. And then moving along, I can set up my stoichiometry relation of the hydrogen gas with the ammonia now. And I know 2 moles of NH3 is equivalent to 3 moles of H2. So when you set it up like that, your moles of H2 cancels out. And then finally, I want to convert these moles of NH3 to the grams of NH3. So this last equality is going to be very similar to what you have for in the first case. So it's going to be the grams of ammonia divided by the moles of ammonia. And I know 1 mole of ammonia is about 17 grams. So when you do this math, we have 6 times 2 times 17 on the top, and divide that by 2.01 times 3. So that comes out to be 33.8 grams of NH3. So this 6 grams of hydrogen is actually capable of making 33.8 grams of ammonia. Okay, so even though this was actually a lower number, it actually made a higher amount of ammonia. So based on those two reactants, the hydrogen and the nitrogen, nitrogen makes the least amount here, which is 18.2 grams of ammonia. So that means your limiting reactant is going to be the nitrogen, and your theoretical yield would be 18.2 grams of ammonia. Okay, so that kind of answers that question. Well, there's an extra question usually connected to these theoretical questions as well. They ask you to calculate the percent yield. All right, so the formula for the percent yield is equal to the actual yield divided by the theoretical yield times 100. Well, okay, so what's the difference between the actual yield and the theoretical yield? So theoretical yield usually comes from the calculation. So keep that in mind. The theoretical yield is going to come from calculations, and those are the calculations we just did. All right, so using the stoichiometry. So keep that in mind. The actual yield actually comes from the experiment. When you actually run the experiment, it may not make the same amount as the theoretical yield. So that's why the percent yield becomes very important. If I give you a simple example, look at whenever you fill your car tanks, and sometimes it gives you the range. It tells you that your car will travel 500 miles before the gas runs out. So that's actually the theoretical yield, the 500 miles. But when you actually start driving the car, does it really travel 500 miles? Probably not. It may travel 450 miles or maybe even 400 miles. So that's actually going to be the actual yield or the experimental yield. So that's the difference. So in these questions, you will always be given the actual yield, all right? And your theoretical yield is going to come from the calculation. So you must calculate the theoretical yield, and your actual yield will be given in the problems. Okay, so I actually know both of those now. So I know the actual yield and the theoretical yield. It's going to be 3 grams divided by 18.2 grams times 100. So let's see what that comes out to be. So 3 divided by 18.2 grams, and that's going to be roughly 16.5% theoretical percent yield. Most of the time, these percent yields are not written in the form of decimals, so I would say it's just going to be roughly 17% as your final answer. All right, so I hope that helps, and I'll post some more videos on these questions.